Tier was set up to bridge the gap between the high-level preliminary sessions and the more detailed technical sessions and cause a lot of conversation. We're trying to bring a lot of new materials and relevant topics to these sessions. They're going to occur every morning at 9:30 in this room and at 2 o'clock in the afternoon, except for Friday. And we hope they cause a lot of discussion. There's a wide range of topics that are hopefully of interest to a wide range of people, both people that regularly attend these forums, and hopefully we draw in some additional people who don't. So with that, I want to go ahead and turn the stage over to Mujib Malik, who's going to introduce the panel.
Good afternoon and welcome on behalf of Revolutionary Computational Aerosciences, which is a sub-project of Aeronautical Sciences project of NASA, of Fundamental Aeronautics Program of NASA. And I would like to give you a little background on Revolutionary Computational Aerosciences. It was about 4.5 years ago that it started with a question that was asked by Lisa Rowe, who was then Center Director for Langley, now Deputy Associate Administrator for NASA. The question that she asked us was an important one. Will CFD replace wind tunnels in 15 to 20 years? And it's important because if we know the answer, one could schedule an orderly infrastructure drawdown and saving costs. So Langley's chief scientist, Dennis Bushnell, and I conducted a quick virtual study where we posed this question to experts from industry, academia, and other government agencies. And the findings are reported in a NASA technical report. The answer, of course, was that no, it will not replace the wind tunnel in that time period, given the investment we currently have. And the key technical challenge is the inability of CFD to reliably predict complex turbulent flows involving flow separation. And so that led to some advocacy for a new initiative in computational fluid dynamics. And the credit goes to Jay Dreyer, who is director of NASA's Fundamental Aeronautics Program, who saw the need and launched a new effort in computational fluid dynamics with the name of Revolutionary Computational Aerosciences. The initiative allowed us augmented research in-house research in this area, and also allowed us to award several research grants, and also allowed us to give a contract to do this study, which was essentially to get stakeholders' input to develop a long-term vision for computational fluid dynamics and develop a CFD research roadmap. And this was a one-year study which was recently completed, and that report will be presented today and then discussed by a panel. And we have, as you can see, put together a distinguished panel. I will introduce the panel moderator, and then he will take care of the rest. And the panel moderator is Robert Gregg III. Robert Gregg is the chief aerodynamicist for Boeing commercial airplanes with technical leadership responsibilities for aerodynamics requirements, processes, configuration development, and compliance while supporting airplane program efforts. In addition to his BCA responsibilities, Mr. Gregg leads the Boeing enterprise CFD efforts. Robert has 35 years of experience in aircraft development, advanced aircraft and aerodynamic concepts, and technology research. In 2011, Robert was the chief engineer of the Flight Sciences, Product Development, and Technology. In that position, he led the Flight Sciences effort on the configuration development for the 737 MAX, 787-10X, 767-2C, and 777X. Prior to that, Robert led the Advanced Design Concept Group within the Boeing Research and Technology Organization, where he was responsible for the technical oversight of multiple advanced aircraft design efforts. Robert's early career focus was airfoil and wing design and use of CFD tools to improve efficiency of computational and commercial and transport aircraft. His first CFD assignment was use of Flow 22 in the definition of C-17 aircraft. Robert?
Good afternoon. I think you'll find that we have a wonderful panel here that has a wide range of perspectives and also a wide range of opinions, and so it should be a lively discussion. But what I wanted to do first is kind of put some things in context. As Mujib said, it actually is 36 years ago this week that I started at Boeing. And one of my first assignments was using CFD to develop wings. And I think back to that time, and CFD was still rather young. You ended up doing a number of designs that you thought made sense, and sometimes you found the holes of the tool. And typically, the decisions would be made in the wind tunnel. We progressed a long ways. At that time, it was also just wing out of a wall. There was really no capability to do engines or winglets. We progressed to the point where today, it's not clear you need the wind tunnel to actually give you the drag prediction. And so decisions are being made by CFD for the complete integrated airplane. And if you go to my chart, this is a chart that's been used before. It's from Doug Ball, but it shows how the CFD tools have really become an integral part of our design process. It touches just about every part of at least the external of the airplane. Now, what has that meant? If you look, it may be an unfair comparison, but you go back to the first generation of jets, the improvement in aerodynamic efficiency since that time is on the order of a 40% improvement. It varies depending upon what airplane you start with, whether it's a long range or a short range airplane. And similarly, the engine has improved on the order of 40% in the same time frame. Now, I'm not going to tell you that CFD was the only reason that occurred, but I think it was an enabler to allow you to understand what's going on and how to apply some of the technologies that were applied in each of the improved products that we put out. What that translates to is that 40% in engine improvement, that 40% improvement in aerodynamic efficiency is millions of dollars per airplane per year that is saved. And you can think in terms of the amount of emissions that is reduced as a result of that too. Now, again, that's going to the first generation of jets. How much of that really is the CFD part of it is, it's probably about half of that because a lot of improvement was made early on going from, for instance, 707s to the 757 and 767. If you go to the next chart, the other thing it does is we've actually been able to use the CFD to reduce the amount of wind tunnel testing, not eliminate. And this chart shows how much wind tunnel time has been reduced from the 67, 777 onto the 87, and it's pretty substantial, and we continue to do that on the 737 MAX and then 777X. And you also look at the amount of time it's taken to do that, and we're actually able to cut cycle time quite a bit as a result of those tools, and not requiring wind tunnel tests all the time. So with that, I'm going to start the discussion with a panel, and first I'm going to introduce Dr. Jeffrey Slotnick. He's a Boeing Technical Fellow in Computational Sciences and Aerodynamics. He's got over 25 years of experience in development, application, and validation of CFD tools and processes for a wide range of aerospace vehicles, including Space Shuttle, C-17, 787, and 747-8, specifically in the areas of engine, plume modeling, subsonic high-lift simulation, transport aircraft formation flight, and wake vortex assessment. He's the current chairman of the High Lift Prediction Workshop, organizing committee and is a proud Texas Aggie. So with that, Jeff.
Thanks, Rob. Can you hear me? Okay. So for the first part of the session today, what we wanted to do was kind of give you a brief overview, and this is going to be fairly brief and very high level overview of the NASA study that Mujib mentioned earlier. Let's see. So I'll start with, obviously I acknowledge the team. We had a very integrated team of experts in CFD that worked on this study. We'll talk about kind of give you a very brief high level overview of the work, talk about what our vision really is, what we came up with. There are some key findings that we found as part of the study. I'll get into those. We did come up and develop a technology plan for moving CFD forward in the future. So I'll kind of touch on some of the aspects of that. We do have specific recommendations that we laid out in the report, and I'll just end with a summary. So as Mujib mentioned, he's the technical monitor for this work. It was, again, a one-year study commissioned by NASA. I served as the PI for the project. Abdi Korodous, my colleague from Boeing, is the project manager. And then we had key people on the actual contractor team, Juan Alonso from Stanford, Dave Domerfall from MIT, Bill Gropp from NCSA at the University of Illinois, Beth Lurie from Pratt and Whitney, and Dimitri Mavropoulos from the University of Wyoming. We also had a number of people, particularly at Boeing and Pratt, that helped behind the scenes, that had a lot of really good input that kind of helped shape the message that we had on the project. So in September of 2012, about a year and a half ago or so, we started this project. It was a one-year contract really to develop an enduring vision of where we think CFD is going to be in the year, notional year of 2030. The idea was to come up with a knowledge-based forecast of the capabilities required to do turbulent, transitional, reacting flow simulations in a routine manner for both design and analysis. And as part of that, we wanted to also sort of develop the plan of how those kinds of simulations would fit into a broader multidisciplinary and multi-physics kind of framework. Okay, so those are really the two main objectives of the study. And so there were a number of different elements of the study that we executed at certain points. Obviously, to begin with, we had to come up with sort of a broad set of requirements of what we think CFD is going to be needed, what types of CFD, what key elements of the CFD simulations are going to be required in 2030. That led to us trying to understand and sort of collect the gaps and the impediments that currently exist and that may exist in the future as well to get us from where we want to be from now till 2030. This led us to the actual vision itself, which I'll get into in a second. And that vision was refined through the use of a community survey, which I believe many of you probably saw that and actually took that survey, as well as a dedicated technical workshop. So with the vision then, we were able to put together a long-term actionable research plan. As part of that plan, we had a technology development roadmap, which you have an example. I think the handout has a view of what that is, and I'll touch on it as well today. What we wanted to try to do with that was kind of capture trends in technology that we see between now and 2030, obviously understand the challenges, and then make the report in such a way that it would provide focus for the broader CFD community to move forward in terms of future research activities. Okay, so we completed the contract in November of last year. There is a NASA contract report out on the web that you can easily download. And I will just say it has a lot more technical detail than I can provide for you today. But it does have also, in addition to just the CFD outlook, a very comprehensive look at high-performance computing and where we think that's going to be in 20 some odd years. We hope that the document will be used for guiding investment in terms of CFD development, both within NASA and within the broader CFD community, as well as serve as an advocacy document to help move along the key critical milestones that need to occur for CFD to be where we want it to be in 2030. Okay, so what is our vision? There's really 6 pillars, I think, here that kind of give you a broad sense of where we think we want to be in terms of CFD in 2030. Clearly, the emphasis is going to be on physics-based predictive modeling. This includes turbulence, transition, combustion, all the key elements of flows that are important to the aerospace community. One thing that we feel very strongly about is control and management of all kinds of errors and uncertainties. We don't really do a very good job of that today. And there's many different sources of errors and uncertainty, physical modeling, obviously, mesh, grid, lack of knowledge of the parameters of a given problem, and then there's natural variability as well in knowing the boundary conditions, for example, of a given problem. We see the need for a much higher degree of automation in all elements, all steps of the CFD process, from geometry creation all the way through post-processing. And we really want the user to have a very minimal interaction with the CFD process itself. We will need to take full advantage of the next generation HPC platforms that we see available in the 2030 timeframe, the architectures of which are going to be very different. They are going to be very different from what they are today. Also make a point of saying that we need to be able to use those HPC systems in a much more flexible way than we are today. And I'll get into sort of the difference what we consider between capability and capacity computing. And then, of course, we clearly acknowledge that MDAO will be a key technology that will be sort of the center point of design, aerospace design work in 2030. And then how does CFD, high fidelity CFD in particular, play with MDAO types of analyses? So these are all kind of elements of the vision that we see in 2030. So now I'm going to very quickly go over some of the findings. There's really 7 key findings. What we've learned, and we believe this as a group, is that investment in basic research and technology has declined significantly over the past decade, if not longer, and must be reinvigorated if significant improvements in CFD capability is to be achieved in the 2030 timeframe. Mujib mentioned earlier that NASA has stood up a program called Revolutionary Computational Aerosciences. This is certainly a step in the right direction. We believe that this particular project needs to be maintained and actually expanded. And I'll have some words about that. Number 2, HPC hardware is progressing rapidly. It's changing rapidly in many different directions. And it's going to be very difficult to sort of predict where that's going to be in 2030. So there are ways of sort of hedging our bets a little bit in terms of CFD development. But we are working on exascale computing right now. But there are other alternative computing architectures that are being designed as we speak. You've probably heard of quantum and some other things. And these potentially will be game-changing HPC platforms for us in the future. Number 3, the accuracy of CFD is really hindered by our inability to compute turbulence separated flows. It's been a major problem from the very beginning, but I think now with our understanding of the RANS framework, we have a path forward. Unfortunately, there is no single silver bullet, is the way I put it. We will continue to work on RANs. We are working hybrid RANs right now, and then of course LES is the more physics-based approach that is being worked as well. And we see a place for all 3 of these methods, I guess, approaches in the next 20 years. Mesh generation and adaptivity, major bottleneck. As many of you have ever done CFD, it takes forever to get a grid, depending on what you're doing, of course. But this is a major impediment to the CFD workflow, and there has been very little, government investment in this area recently. And so what we're looking for is, streamlined processes to get from geometry to a grid. And ultimately, what we really want is never for the practitioner, the CFD practitioner, to never actually see the grid itself. Okay, it would just be a natural part of the solution process. Number 5, even with that speed of HPC that we expect. We're still going to need algorithmic improvements in terms of better robust convergence, scalability on HPC, and then, of course, uncertainty quantification. And number 6, we're starting to see this now, but as HPC power increases, we're going to be able to do more and more with CFD, and we're going to be creating bigger and bigger data sets, and how we manage all that data is going to be very, very important in making actually design decisions. So we'll have to come up with better methods to actually manage single, large simulations, as well as large matrices of simulations, and then how we merge CFD data with other sources of data, like testing, flight testing, ground testing, whatever. And lastly, obviously to enable MDAO, we're going to need significant improvements and actually breakthroughs in many areas. CFD solver robustness, obviously, and automation is going to be a key to that. How you do the coupling between CFD and the other disciplines is going to be a major key area that needs to be improved. So I have to come up with standards for that. And then computing and propagating sensitivities and uncertainties, not only in the CFD element, but also in the other disciplines. It's going to be a key component in having a really robust MDAO type of capability. Okay, so as part of the technology plan, we came up with this concept of grand challenge problems. And these problems sort of represent step changes in capability. And the idea here was to put a goal so far out there that it would be something you can drive to, and it may not be achievable in the 2030 timeframe, but it's something that you can incrementally work to. Okay, the 4 challenge problems I'll get to in a second all represent elements of the major NASA missions, as this being a NASA-funded report. So number 1 would be the LES of a powered aircraft configuration across the full flight envelope. So this would be, say, a commercial airplane, full configuration at all, obviously cruise point, the high lift point, at any point in its flight envelope. It could be maneuvering as well, so it could be transient. Number 2 would be an off-design turbofan simulation of a complete engine. Okay, this would include a full combustion, rotating machinery, conjugate heat transfer, all the different things that are needed to do a full engine simulation. Number 3 would be MDAO of a highly flexible advanced aircraft configuration. Here we'd be focusing on the tight coupling of different disciplines, particularly aero, structures, controls, maybe others, in the sense of a new advanced aircraft configuration. And then lastly, the probabilistic analysis of a powered space access configuration. Typically, a spacecraft, you don't get too many chances to do ground testing or flight testing. So what we want to try to do is understand and manage the uncertainty and the errors in our CFD processes, and that would be a good opportunity to do that. Okay, so I'm not going to belabor the roadmap, but we did spend a lot of time in developing what we think is a reasonably complete roadmap between now and 2030. You've got a copy of that I think that you can look at in more detail. I'll just touch on the high points here. So the idea here was to identify improvements that need to be made in the 6 areas: HPC, physical modeling, algorithms, geometry and grid, knowledge extraction, and then MDAO. We have swim lanes for different technologies colored by technology readiness level. Green means it's sort of high technology ready, high TRL level now. Yellow means moderate, and red obviously is not really ready for prime time. So you see a lot of technologies red on the left-hand side of the chart, and as we improve the technology, they change from yellow to green in many cases. With HPC, what we see is really 2 swim lanes, one for exascale, which is what we're really working on and working to today. We have a sort of a development plan to get us to where we need to be in 2030. in terms of massive parallelism for CFD codes. However, we do have the revolutionary types of computing that are being developed, and what we recommend we do is every 5 years or so reassess, where we stand with those computing platforms and see, well, is quantum, for example, able to do CFD type problems? And if so, you make some adjustments to your investment profile on the HPC side. And one thing that here we have what we call technology demonstrations. These are the blue stars. These are sort of demonstration problems that lead to the grand challenge problems. So these would actually be achievable given the amount of technology that we have developed up to that point. And so we have them scattered about on different swim lanes, and they're all kind of connected because in general they're integrated kind of test problems. Okay, so this gives you a sense of where we're going in terms of the actual technology development details in each of the different areas. Okay, let me just get to the recommendations. There are 6 major recommendations here. So as one of the findings stated, we do not have enough base research and technology development. We recommend that NASA develop a project or a plan to do that. It's important for a number of different reasons. Obviously to execute the development challenges for CFD and the grand challenge problems. As Rajiv mentioned, we do have a revolutionary computational aerosciences project currently under the Aeronautics Research Mission Directorate at NASA. What we are proposing to do here is strengthen that by adding in elements of the other projects under transformational tools and technologies. So for example, in the blue here, the things in white are being worked today. So there are NRAs out there for turbulence modeling, transition modeling, and numerical algorithms. We recommend adding in then oversight and collaboration in combustion, HPC, geometry and grid, knowledge management, and an MDAO. Okay. All this, of course, would require a huge amount of collaboration, not obviously within NASA and also externally outside of NASA. Number 2, NASA should develop and maintain an integrated simulation software development infrastructure. And what this really means is there are 3 elements to this. When we say software development, we're talking in-house simulation capability. It really should be superior to what exists outside of NASA, even in academia and industry. It would cover the full spectrum of vehicle phenomena in cases at NASA. And it's really critical to develop that kind of capability and expertise in-house so that you understand the principal areas of development that needs to happen between CFD and, say, an HPC. We need better software development processes. They need to be more streamlined and improved. This will, we're talking about version control and many other modern software programming activities. NASA has developed a number of different CFD tools over the years in sort of an ad hoc fashion, and so we believe that this will, enhance the way CFD is developed and transition to, say, industry. And then, of course, CFD standards and interfaces. I've touched on this, not only for MDAO, but also for geometry and grid and other areas. There are many different ways of doing the different elements of CFD, and we need to kind of standardize that. Okay, number 3, HPC systems should be made available and utilized for large-scale CFD development testing. Okay, we make the distinction between capability, so being able to run very, very large simulations on thousands of processors, for example, on an HPC, versus capacity, which is more throughput, being able to run thousands or hundreds of thousands of cases within a certain amount of time. We want to be able to utilize HPC in the future to be able to do both, and both will be required to really improve the overall CFD technology. We think NASA can obviously leverage existing internal resources as well as national HPC resources at the national labs. And of course, we want to provide access to these other novel systems as they become available so that we can see if CFD is plausible and possible on those systems, you know, between now and 2030. Okay, NASA should lead efforts to develop and integrate, execute integrated computational and experimental testing. This is something that the group felt very strongly about. You know, NASA's in a very unique position where they have expertise in CFD, a very deep expertise in CFD, and world-class experimental facilities. We need to be able to look at both doing integrated computational and experimental testing for building block cases as well as more complicated geometry. So having both of those is really important. And again, NASA is uniquely positioned to take advantage of the synergies they have internally to make this happen. Number 5, NASA should develop, foster, and leverage improved collaborations with key research partners, both obviously within the United States, internationally as well. And that would include the broader scientific community, high-performance computing community, as well as aerospace engineering, okay? So this would include, like I said, the US government. The emphasis should be on funding both engineering and applied, applied math and computer science to make the case for improved CFD in the future. One of the things that we mentioned in great detail in the report is the concept of sponsored research institutes. iCase, for example, is one of those that many of you are probably familiar with. Many of these exist across the globe. We find that these are potentially the best possible path by which you can bring together the collaboration that are required to move CFD forward. And then, of course, the last here is NASA should attract world-class engineers and scientists. I think that goes without saying. There are probably many ways of doing this. You know, obviously, having the key people will make the CFD development that's needed in 2030 a reality. But we need to be able to obtain these people, train them, and nurture them, and keep them focused on CFD. We can do this in many different ways: fellowship programs, visiting research programs, and then visiting students. You know, should be given the opportunity to work on meaningful, elements of the CFD development, and really towards the solution of the grand challenge problems. Okay, that will keep the workforce really kind of focused and engaged in the development of CFD. So in summary here, CFD is obviously heavily used now, as Rob was mentioning, in industry. It is a key element to doing a lot of the key design work that we've been doing now for several decades. However, it doesn't work everywhere to the accuracy level that we want. So issues still persist, okay? To effectively use CFD in all phases of the design process, in all corners of, say, of the design space, we have to make significant resource investment into the future in terms of CFD development. So I've given you a very broad, brief overview of the Vision 2030 CFD study. I welcome you to read the actual report. It's fairly lengthy, keep you up at night, but it has all the detail that I couldn't touch on today. And then finally, once we have what we call the transformational CFD capability in hand, it will enable us to do the things that we really want to do. And one of the things we're going to talk about today is certification by analysis. So that's all I have.
Thanks, Jeff. So wow, it's a challenge there. Cert by analysis seems like a pretty far out there concept. But it reminds me, since the Stanley Cup just was completed, I have to kind of refer to Wayne Gretzky, the great one, who said you miss 100% of the shots you don't take. So here's a shot that we're going to take and see where it goes. Certification, Only thing more expensive than wind tunnel testing is flight testing. And so the value of getting to the point where, at least from industry's perspective, where you're able to do some activity, certification activity by analysis would be a very big deal in terms of the cost and the time it takes to get the airplane certified. I know on the space side, we also have used very successfully the ability to use CFD to predict, at least in the return to flight, we were able to predict where the risks were really coming from the foam that infamously caused a stop of launch for the shuttle. So we know that CFD can be very helpful in looking at those kind of problems. So now to get a different perspective, we're going to have our engine company partner from Pratt & Whitney. It's Steve Morford, who is responsible for the engine system functional integration, performance and operability, aerodynamic design of a secondary air system, emissions and noise characteristics, and controls and diagnostic systems for the Pratt & Whitney's large commercial, military, and power systems products. He joined Pratt & Whitney in 1986 as a combustion engineer and has held various positions working his way up the line. He holds degrees in mechanical and aerospace engineering from Clarkson University and Rensselaer Polytechnic Institute. Steve's accomplishments include leadership role in development of the PW1000G geared turbofan, where he received the United Technologies George Meade Medal for Outstanding Technical Achievement and Aviation Week's Laureate Award in Aeronautics Propulsion. Additionally, he's been a recipient of the ASME Hartford Section Distinguished Engineer of the Year Award. So Steve. Steve's not, he doesn't have any charts, so he's going to talk.
Thank you, Rob. So Rob told me I had 5 minutes max, so I said a chart longer than 5 minutes. What I wanted to get across today was a little bit about three themes. First is value of CFD from an industry perspective. And then the perception of CFD within the industry. And then thirdly, the limitations we see in application of CFD to gas turbine problems. So first, the value. As Rob mentioned up front, the industry has seen tremendous fuel efficiency advantage over the last 30 to 40 years. The reason is not all aerodynamic efficiency. Materials play a very big role in that. Thermodynamic cycles play a very big role in that. So that benefit, though, there is no doubt CFD can be attributed to a large portion of that. The insight the engineer gains from understanding the detailed aerodynamics characteristics as they apply CFD is invaluable in terms of understanding and advancing the state of the art in component design. Current engines typically are about a 40 to 50 overall pressure ratio, and they do it in fewer stages than engines that are 30 pressure ratio from 20 years ago, about 10 to 15% fewer stages. And that benefits airlines from the standpoint of fewer parts is lower cost, lower operating cost, higher efficiency. A value that we don't always attribute to CFD. Secondly, from the standpoint of the engine manufacturer itself, that insight allows goals and objectives to be achieved much quicker and much more reliably than they have in the past, particularly in the 1980s and 1990s, where CFD was really at its early phase of application, and much of the development was done through experimentation. In our PW4000 product that is on the Boeing 767, 747, we did 40 high compressor rig tests. 40 high compressor rig tests. Typical high compressor rig test is multi-million dollars. In our latest geared turbofan product, we did 2 high compressor rig tests. Gives you an example. You can take that forward to, we were talking about separated flows. There's one component of an engine that is designed to feature separated flows by intent, the combustion chamber. And in that, we've seen similar advancement. I started in that area, so I have a particular affinity for it. But in 1986, when I started, we did no CFD on combustors. By 1990, we thought we were really sporty, 100,000 grid points on a mesh on a Cray XMP supercomputer. And the results were interesting. It was RANs, no unsteady nature. We turned the turbulence model up to be 60% turbulence to try to get a reasonable answer, and we didn't. But not long after that, we started using unsteady RANs, made the quick transition to the fact that wouldn't work, and then we moved to a hybrid LES schemes. And those are in production today in our CFD methods. And we've seen advances of 75% reduction in the amount of tests we do to develop a combustor, and 60% improvement in the emissions of a combustor. So huge advantage from the company's cost structure, as well as the environmental compliance of the engines. When you take a step back and you ask, what is the perception of CFD within the industry? The perception is one of a love-hate relationship. CFD is critical to the success of our industries. We could not be where we are today. Before we came up on the panel, we were talking about how could we design an engine or an airplane today if we didn't have CFD. I think a lot of us would realize that we couldn't do it. It would be very painful. The business would not withstand the investment required to go do it by old methods. So from that standpoint, it's vital for our industry. That's the love part of it. The hate part of it, it doesn't always give you the right answers. And understanding how to decipher whether the answer is correct or not, the knowledge extraction, I think, was the term used in the study, an excellent term. How do you decipher whether you're getting a realistic answer out of CFD or not? As we advance to much more application of CFD, the data derived from CFD is so overwhelming to the engineer, can they actually dig deep into the solution to determining the governing physics that have produced the result they see in the one-dimensional number they get, the pressure distribution on an airfoil surface, et cetera? Do they understand why the code predicted that answer? That is very challenging right now. And it's a real gap going forward when we start talking about further advancement in high-performance computing and multidisciplinary optimization. And those errors, because of the huge success we've had with CFD, we've also taken a much more aggressive position towards developing engines. We do it in a shorter time scale than we ever have, about 25% shorter. But because of that, when we do have a failure with CFD, it becomes a really painful experience. And it's happened. So that gives you an overview of the benefit and the perception. Let's talk a little bit about limitations of CFD in jet engines. First, I'll start with the range of applicability. Probably the biggest limitation there is. Every component in the engine, every airfoil, every secondary air system, every combustion, every bearing lubrication system on the engine is analyzed with CFD today. Every one that can be is. It's generally analyzed at its design point 100%. It's off design that we run into problems in particular. In combustion systems, at design points, basically cruise or takeoff, the chemistry is so fast relative to the mixing of the fuel in the air that it's a aerodynamically limited problem, and chemistry is not that big a term, frankly. So it's relatively computationally tractable to do. When you look at high altitude starting of an engine, a certification requirement, instead of the pressure and temperature in the combustor of being 40 atmospheres and 1,000 degrees Fahrenheit inlet condition, it might be 4 psi and minus 70 Fahrenheit. And can you light the fuel? It's a certification requirement, not computationally capable today. So it gives you an idea of the range of applicability we need. In compression systems, the front of a high pressure compressor, it's not unusual for us to see velocity triangles swing by 40 to 50 degrees between design point and idle. And how you handle that, the variable geometry, akin to the variable geometry on a wing, is a very challenging computational problem. And understanding how to predict that in a multi-stage high compressor is one of the limitations we have today. And the last thing I'll mention on this is speed within the design cycle. We can throw all the computers in the world at these problems, but for the industry to use them to actually affect the products we're designing today, the speed of the computations must be within the design cycle, within the design iteration cycle. So when we design an airfoil on a high compressor, it's not just the aerodynamicist designs the shape of the airfoil. The structural analyst has to determine the stress on the airfoil. The manufacturing engineer has to determine how he would make such an airfoil. And that is iterated hundreds of times in approximately a 9-month interval for us to develop a high compressor design. How do I affect or insert higher fidelity analysis that off design, aerostructural interaction analysis, such that I can be within that design cycle and not extend the design cycle? That is one of the real challenges for us going forward, is capability and speed of the capability within the design cycle. Okay? Other problems that we face that are limiting are, as I mentioned, aerostructural interactions. Aeroacoustics is a huge issue. Aeroacoustics conference going on right now, so I thought I'd mention that. Thermoacoustic instabilities. Heat release, acoustics, aerodynamics simultaneously. Conjugate heat transfer. All are the types of problems that are going to require significant advancement in computational capability, multidisciplinary analysis, for us to really progress to the next generation of jet engines. So with that, I hope I've given you an overview of some of the challenges from the engine manufacturer perspective. Thank you.
Thank you, Steve. So you've heard some perspectives from industry, and I'm going to call an audible here. So Juan, I hope you're ready. We're actually trying something new. We're going to have audience participation through polling. And I wanted to go with the first polling question. Juan, if we can do that. So you can respond either by texting to 22333 with one of these answers, and I'm going to read the question in a minute, or you can get online with your smartphone or laptop to that location, and you should be able to respond to the poll. So the question is, the Vision 2030 CFD study prescribes a set of specific recommendations to help guide technology development within the CFD and scientific communities. Given limited budget resources, what do you believe should be the main focus of future CFD development? And I want you to pick two of those. So, we're beginning to get some response. Neck and neck. All right. So the way to interpret it is the longer the bar is, the more people are voting for those particular items. And it's a race. It seems like it keeps moving around, so that may tell you that given enough time, things might start to even out a little bit. Although it looks like flow physics and algorithms has a pretty good lead. And productivity process, maybe? So we'll let this continue on. We're going to have more of these as we go through the session. And then after we go, we're going to get into question and answer, and we're going to allow you to start asking questions. So with that, I'm going to now introduce the next panelist. Dr. David Schuster is a NASA Technical Fellow for Aerosciences within the NASA Engineering and Safety Center, located at NASA Langley. He has over 35 years of experience in the aerospace industry, and 30 of those devoted to the Aerosciences discipline. Interestingly enough, in his bio, he mentions that he was involved as part of the NASA engineering team that provided detailed design recommendations to the Chilean government for the rescue capsule used to save 33 trapped Chilean miners in 2010. So that was a pretty cool effort. Let's see, Dr. Schuster began his career as a scientist at Lockheed, developing and applying computational aerodynamic tools to a wide range of problems in flight simulations. He went on to Georgia Tech Research Institute Aerospace Laboratory to help form a new experimental computational aerodynamics and aeroacoustics capability for the lab. And he earned his Bachelor's of Science degree in Aerospace Engineering from the University of Cincinnati and his Master's and Doctorate degrees from Georgia Tech. So he's local right now, back home. And he joined the American Institute of Aeronautics and Astronautics as an undergraduate student in 1977. So he's had continuous membership since then. He's currently an associate fellow of the IAA. So with that, take it away.
Thank you. Thank you, sir. I'll come on up to the podium because that's what I had in mind from the start. So I'm here as, I think, your token space advocate. I spent the first 25 years of my career, though, in the aerodynamics or aircraft portion of the Aerosciences discipline. But then 7 years ago, I joined this organization called the NASA Engineering and Safety Center. And as you can tell by the chart that I've put together, they've broadened my horizons considerably. So what I've been asked to do is kind of talk about how NASA or how CFD influences our work at NASA, at the agency, and I'll just say that it permeates our day-to-day life within the agency, and it's not all about the typical types of applications that we're used to seeing probably at this conference and certainly for CFD in the past. And our applications range everywhere on this chart from the upper left-hand corner, which is our aeronautics traditional type applications, rotorcraft, fixed-wing aircraft. But about the time I joined the NESC, we got into this program called the Constellation Program. We were looking at developing the Orion Crew Module and the Ares launch vehicle. And suddenly we found a whole new set of problems out there. And I'm going to try and dispel a couple rumors, or at least maybe put a counter argument to some of those rumors. And the first is that space is all about hypersonics and entry, and it really isn't. What I found out when I got into this is that the majority of the applications that drive me crazy are the same ones that I had in the aircraft: low subsonic, high angle of attack, transonic flow. All the things that have plagued me throughout my career are the same things that are killing us in the space on the space side today. So to give you an idea of some of the applications that that work on a day-to-day basis, everything from the launch vehicle side, from low speed, high angle of attack, stage separation flows where we have to predict the trajectory and the movement and the dynamics of a launch vehicle, to ground wind loads while the vehicle's on the pad, high angle of attack, low speed aerodynamics, to launch abort systems where we're at anywhere from subsonic or zero velocity on the pad all the way up to Mach 4, and we have to do an abort. And one of the big issues here is transonic abort. And here we have large areas of separated flow, plume interactions, plumes in the separated flow, about as nasty a flow field as you can imagine. We get down into the lower left corner, we start talking about how we're going to bring some of these vehicles home, and we're talking about flow on the parachutes, some of it transonic, all of it separated. When we talk in the aircraft world, we're usually in regimes where separated flow is the enemy, and so we're trying to stay out of those regimes as much as possible. And when I hear things like we can develop databases without having to go to the wind tunnel, or we can develop databases in our CFD with only a few spot checks on the data from the wind tunnel. I think those come from the fact that you're not having to do separated flow on a day-to-day basis. And that's what we're dealing with in the space world. We don't, our nominal flight involves unsteady separated flow, and that's going to become a recurring theme I think you're going to hear throughout the day. As we get down into the bottom part, we start to get into some really off-the-wall space applications. Everything from the Cassini spacecraft trying to make a low pass on Titan and fly through its atmosphere, and we're having to tell them, is that spacecraft going to tumble, or does it have enough reaction control system to keep it from tumbling as it goes through that atmosphere? We're out there computing the drag on the International Space Station so we can predict how often we have to do a burn to move its orbit and get it back and keep it in LEO. And then finally, on the far end of the chart, we get into the ground system applications. And these, quite surprisingly to me, have consumed a large component of my time and the resources that we go to look at. Everything from ground wind loads for launch vehicles to acoustic and ignition overpressure loads on test stands at our Stennis Space Center down in Mississippi to the flame trench flow field and the environments that are being seen on the launch pad as a shuttle solid rocket booster ignites. So that's the range of problems that we deal with, and I kind of put the aeronautics up there in the upper left-hand corner just to kind of give you an idea that when you start looking at all of NASA, it is a subset, and it may even be a very small subset. So if we go to the next chart very quickly. So from seeing all these types of problems, I come up with a state of the discipline every year in my job. It's the top Aerosciences challenges, and these are my top 3 that I, in order of difficulty, and I'll just run through them very quickly. Aero-plume interaction prediction. This is looking at aero-RCS interaction as well as main engine plume interactions with the aerodynamics. Again, a lot of it going into separated flow. Number 2 on the list, and close to number 1, is unsteady separated flows of all kinds, particularly in the area of aeroacoustic and buffet environments for our launch vehicles and for our spacecraft. And then finally, aerothermal predictions, the more traditional thought that you might think of when you're talking about a space application, ablator performance, boundary layer transition. Unstructured grid aerothermodynamic analysis is keeping that kind of behind the current state of the art in general performance. Go on to the next slide, please. So if we look at the current state of the art for us on the space side, this is a fairly recent buffet calculation where we're looking at the buffet environment on our Space Launch System, SLS. It's a 2-solid rocket booster with 4 shuttle main engines as the core. And there was a strong buffet at the forward booster interface where it attaches to the core stage. We, on a whim, we had a little project to take a look at see if CFD could do anything here, and we did some fun 3D delayed detached eddy simulation calculations. And lo and behold, we found out that we predicted pretty well with the wind tunnel. But just to give you an idea of what we're talking about here, we're doing a delayed detached eddy simulation. It's about half the vehicle, 36 million grid points, about 1 million CP hours to get a few seconds of data, maybe 2 seconds of data on the CFD. Compares really well with the wind tunnel. If I take the total cost of that simulation in full cost, just the computer hours, $50K to generate this solution. So that's the second rumor I need to dispel. I heard somebody say the only thing more expensive than a flight test is a wind tunnel, or more expensive than a wind tunnel test is a flight test. In our realm, the only thing more expensive than a wind tunnel test is a CFD analysis and a flight test. So our CFD analyses, when we see on the space side, are not necessarily the cheapest things around. And finally, my last slide is if we can go to the last slide. We've already talked about, this is my CFD Christmas list. We go through the first 3. I think those 3 Jeff has already touched on. We'll drop right on down to number 4, and that's looking at simulation wall clock times that match or exceed real-time flow physics. I think that's a real challenge for us and what we really like to see. And then getting into number 5, I think we need to dispel this this thought of when is CFD going to replace the wind tunnel, because I think CFD can do so much more than the wind tunnel. And so I think we need to be doing calculations and pressing towards a capability where we don't run CFD like it's a wind tunnel anymore. I think in the space side, we're finding that the CFD is not very well suited to developing large, massive aero databases. What it is capable of doing is things that we can't do in the wind tunnel. Rapidly accelerating vehicles, things where we don't have to sit on a point forever, doing things at flight scale. So I think these are the things that we need to be pushing the CFD towards, and not so much how are we going to run the CFD like it's a wind tunnel, but how are we going to take CFD to its full potential. So that's my keys.
Thank you, Dave. Reminds me, a number of years back, one of my employees, who's out here somewhere, Abdi co-introduced, we were talking about what is required on space launch calculations, and he reminded me you have to be able to go from 0 to hypersonic and everything in between. And so it is a very wide-ranging problem to worry about. At 0, it's even sitting on the launch pad and looking at the plume effects while it's there. So it is a very complicated problem to try and solve. So now moving on to another perspective, we have Dr. Cord Rosen. He's got his master's degree and PhD from the University of Braunschweig. He currently is the director of DLR Institute of Aerodynamics and Flow Technology, and actually is acting head of the DLR facility for flight experiments. And so we thought we'd get the European view of what CFD is all about. Thank you, Cord.
Yeah, thank you, Rob. Well, first of all, I'd like to thank the organizers for having the opportunity of taking part in this panel discussion here. And I also, on the second part, I also like to thank them for this organization in that part, that they scheduled it such that it didn't interfere with the match Germany-Portugal in the World Championship, so, where everything went smoothly as far as I know. But this is not the issue of today. As it was mentioned, I'm also heading the DLR flight test department, at least as an acting head now. And I'm also a member of the advisory board of the German-Dutch wind tunnels, and I'm also a member of the supervisory board of EDW, and I have certain reasons of mentioning this here in the very beginning. Since I started my career as a CFD developer, meaning really developing codes and things like that. And today we are talking about the vision, how is CFD going to evolve in the future? And I'd like to present a brief vision for aircraft design, and not only design, but also its realization based on numerical simulation, since I think we have to talk about numerical simulation as a whole, not only about CFD. Next slide, please. Next slide. Well, what is the current status of numerical simulation? When you look back, I think one can state that CFD has evolved significantly over the last 35 years. And well, for example, if you look at the design of supercritical airfoils, which at the 60s and at the 70s was, put it this way, a well-guarded secret in industry how to apply this to aircraft or to aircraft design. Today, it's commonplace. It's done by students. So this tells you a little bit how far CFD developed. I think it's now complementary to wind tunnel testing and also flight testing. And it may be considered now as a mature tool for configurations at their design point in the flight envelope. And with this, I'd like to go to the next chart, please. That's a perspective. What is really the perspective of this, what we call a virtual X-craft at DLR? I think what's required is that we go towards the full flight envelope, meaning we have to tackle all the physical things we encounter there, as it is transition and separation, as it was mentioned already. We have to include, first of all, the structural response, and then also flight controls. And flight control today is an inherent building block of designing aircraft. So we are not talking about this cruise point, which you can see there in red, but we are talking about now to explore the whole flight envelope of the aircraft. This is where we have to go. Please click one further. And with this, if we really want to leverage this potential, What we then have to face is we have to ensure that we have reliable and efficient simulations, meaning with respect to the complete aircraft, we have to deal with complex flows and a huge number of cases to treat. These will be multidisciplinary simulations, and we have to make proper use of the HPC resources. Everything was already touched upon in this CFD Vision 2030 report. Next slide, please. Well, and what is now the potential of that? First of all, it's the design. You know, all these things like time reduction, cost reduction, risk reduction. And I borrowed a slide, I found it on the internet from the Defense Acquisition University, which gives you an overview of how cost evolve. On the one hand, say the real cost. This is the brown region there. As you can see, over the development phase of an aircraft, these costs increase gradually. But if you look in the design process, in green you can see the committed cost, meaning that these are the costs you commit by your decisions you do in the early phases of design. And there you can see that this has a very steep slope, and essentially that is where CFD and numerical simulation in the whole is really showing its potential. This is where we have to head at. And further to this risk, time, and cost reduction, there's also the possibility by numerical simulation to push the technical parameter, meaning we can experiment with new technologies already, first of all, in the computer before we go towards wind tunnel testing and flight testing. And also some issue, I think, at least from my perspective, which is quite important with respect to, again, numerical simulation as a whole, not only CFD, is knowledge preservation. If you look at the design cycles of today's aircraft, well, in the past, whatever you define as past, being it World War II, being it the post-war era, their aircraft were designed more or less on a monthly, yearly basis. Today, it's 5 years, 10 years. Maybe as an engineer, you will have, if you're lucky, 2 or 3 really full aircraft programs in your whole lifetime. How do you develop experience? How do you preserve the knowledge? And I think this is where also one of the facets of the value of numerical simulations comes into play. So that's the design phase. Well, now at the end, I come to the realization phase. One should not only look at the design phase, but also at the production issues. With respect to numerical simulation, what you can do is you can early on consider the requirements of specific production issues. You can also try to simulate the first flight in the computer, meaning you get information about performance and also handling qualities. That's what I try to express with characteristics prediction. This will enable you to save significant amount of time and cost. And it was also mentioned certification as a vision. Numerical simulation may serve here as support and even as a substitute in certain parts of the real certification process. And perhaps to give you one example, that this is really not a myth, as somebody mentioned in the morning, but there's really some proof that it is possible. As I'm now heading the flight test department, we had some flight testing being done at the end of the year, and we encountered several problems there in this flight testing. And by using CFD in a very quick way, we were able to remove these or redesign certain parts in the instrumentation we had to use on our test aircraft. And this enabled us, in the certification process, to change certain parts and then do the certification process. So if you use these tools complementary, this is, I think, where you can get the real value from. And well, with this, I'd like to conclude. Thank you. Thank you,
So now we're going to move to a university perspective, where we tend to be even a little bit more forward-thinking and looking at different ways of approaching some of the problems. And we have Dr. Parviz Moin, who is the Franklin P. and Carolyn M. Johnson Professor of Engineering and Director of the Center for Turbulence Research at Stanford. He's directed both for the Department of Energy and NNSA for centers at Stanford over 2003 to 2014 time period. He is the co-editor and annual review of fluid mechanics and associate editor of the Journal of Computational Physics and the Physics of Fluids. He is a fellow of AIAA and the American Physical Society. He is a member of the National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences. And with that, Parviz.
Thank you.
All right, we can go to the next one. I have to put my glasses so I can read this. I just, one of the questions, the first question was posed to us was, tell us the value of CFD for you. And my view as being a member of academia is that we have always thought about CFD, especially high fidelity CFD, for using simulation to ask what-if type questions, things that would be expensive to do in the laboratory. Also, possibility of exploring concepts rather than evolving and perturbing the existing concepts, configurations. And again, using CFD to explore cause and effect relationships. So these are some of the things that ever since the beginning of large eddy simulation in engineering in the 70s, we got into it to be able to answer some physics questions and mechanistic questions about what causes what. And that, to me, is the main value of CFD. The other part that I hope that I'll be able to expand on here, having been involved with the Department of Energy's National Nuclear Security Administration, is that they also have a unique perspective, which I think this Vision 2030 could benefit from. And as you know, because of the Nuclear Test Ban Treaty, DOE has been looking into computational science to be able to do certification through simulation, and also under extreme conditions and involving multiple physical scenarios. That is, I think, off-design conditions and accident scenarios, et cetera, is what the goal of DOE has been, NNSA has been for some time, and I hope we can bring some of that here. Can I have the next slide? So the main part of it, my talk from here on has to do with large eddy simulation and the role that large eddy simulation can play in this setting. So I have this slide from Boeing that shows you the number of wing tests required for the various aircraft and as a function of year. And this has been pointed out here and also in the past has been a primary motivation for CFD. That with the advancement in CFD and computer hardware, the number of wing tests, for example, will be reduced. And here, I think that trend was very much true up to about 20 years ago. And in particular, as you can see, starting with 1995 and the 777 Boeing, where we required about 11 wing tests, and to 2005 for the 787 aircraft, I think that number stayed the same. Now, we can have many interpretations of this, but my take on this chart is that the accuracy of the standard engineering tools for external aerodynamics and in CFD have plateaued. Most of these techniques, all of them, are RANS-based techniques, and RANS-based techniques have a certain limit upper bound on calculations because they are not based on first principles. There are a lot of phenomenological reasoning that goes into coming up with a good RANS model. In the same period, from 1995 to 2005, the computer power has increased by a factor of 1,000. While the utility of CFD, at least in this context, has stayed the same, the computer power has increased by a factor of 1,000. And what I think is we should look into techniques that at the very least can guarantee that the more brute force, if you will, or computer power you throw at it, the accuracy would increase. At least that limiting process should exist. And I think LES is one technique that ensures you that if you start adding more computer power, your resolution and your accuracy increases. Can I have the next slide, please? So this is the chart that I mentioned earlier. Every 7 years, the computer power has been increasing by a factor of about 100. So what this means, in other words, if you are conducting calculation on 200 cores, 200 processors today, you feel the same way about it in 7 years with using 20,000 cores. Okay. So the use of 20,000 cores will be as routine as it is today with 200 cores. Can I go to the next slide, please? So the top part is what I just basically mentioned, that the RAND's accuracy has plateaued. We should seek techniques that have a direct path to first principles. That means that it would guarantee accuracy. And next, I want to give you my take on the statements that are in the report itself, the Vision 2030 report regarding LES. Specifically, I feel that the cost estimates for LES that are provided are extremely pessimistic. I think in the past 20 years, mostly because of the National Nuclear Security Administration support, there has been groundbreaking advances in high-performance computing, in numerical methods, subgrid scale modeling, large eddy simulation, and I think LES now, as a result of a lot of these investments, have become quite an effective tool for industrial use and especially for multi-physics engineering analysis. Next slide. Here is my, on the top, there is a table from the Vision 2030 report that estimates what the cost would be or number of grid points required to do a wing, essentially with the aspect ratio of 1 chord at various Reynolds numbers. Now, and there is on page 12 and 13, there is a statement that LES dominant methods for the range of engineering problems of interest will likely not be feasible in 2030. So I think that we are ready, in fact, right now to apply this technique. This is proof of my statements is the table from the actual calculations that we have already performed using LES on separated flows. And the same kind of airfoil estimates that are given there, we have actually performed, at least the top one here, and we can scale the mesh requirements for the additional Reynolds numbers. Most of the discrepancy between our estimates and the report's estimates has to do with the handling of the laminar section and the prior to transition. Okay. So let's go on to the next slide. And as I said, we have been there and done that. These kind of calculations with good accuracy, with no tuning parameters, which is, I think, absolutely critical for certification, that you can predict experimental data. And this is the airfoil NACA 4412, angle of attack, where Langley workshops have documented that the many RANS techniques all fail on this. And to be able to predict that out of the box, I think, was one of the achievements that large eddy simulation, wall model large eddy simulation has done already. Can I go on to the next slide, please? So there are other aspects that I think, since we are talking about vision for the future and what we need to do, to advance to the next state, I think we have 100 times discrepancy between what we have right now. I just talked about that, about the reported calculations. But there is also at least a factor of 10 that we can achieve because, and that should be a goal for a BAA from government, for example, that most practical codes right now operate at 3 to 5% efficiency on the major supercomputers that exist today. So there is this huge gap that requires blending of computer science and numerical algorithm development to at least get another factor of 10. Combining these two, I think the report is at least a factor of 1,000 too conservative right now, and we should achieve, these goals are realizable that in the very near future. I think with the 5 exaflop machine that DOE has in mind, is somewhere between now and 2030, we can both design and optimize aircraft design, wing design, et cetera. And I think multi-physics wall model LES in combustors is already being used in, as we heard, in propulsion industry. Okay. Next. I want to show you this supporting slide that I mentioned. I had the exponential growth of computer power, but the red curve at the bottom here, it shows you how the efficiency of real calculations on real codes plateau. Recently, we participated in competition for, and the report, I think, mentions this calculation. The top curve is the one that, a recent calculation that won the Gordon Bell Award at the Supercomputing Institute, where they reached 70% peak. Put a lot of effort, optimize the CFD code to be able to use state-of-the-art machines that are available right now with 70%. We are still in a 3 to 5% ourselves in this efficiency. So that is a good goal for the Vision 2030 to go and achieve that, to get into the existing algorithms and blend it with computer science to be able to get to the top. Next. We did a calculation recently on 1 million cores. This is a supersonic jet exhaust with chevrons that we did, and excellent agreement with the experiment on the spectrum or far field noise and the near field noise. Again, with no tunable parameters, which I think is essential for certification, being able to do that. And finally, I want to say that this calculation, next slide, please. This 1 million core calculation was made possible. In fact, we jumped on this calculation, on this endeavor within 1 week. The codes were ready. So when the Sequoia supercomputer came, a Livermore was put on it. We were able to do, within 1 week, we did this entire calculation. Our codes were ready and installed and ran within 1 week. I think this was made possible, and I want to pitch on one other aspect of the report about the future funding. We were able to, because we were privileged to have the sustained support of Department of Energy, National Nuclear Security Administration, for 15 years now, at the cost of $4 million a year, has been a substantial investment, long-term. We are able to attract the talent in computer science, in numerical methods, people who understand the physics, put them all under one roof, which I think is essential, to have these various groups to work under one roof to interact. And now we have, I think, capabilities to do hydrocarbon chemistry, two-phase flow in complex geometries, noise, aero-optics, optimization, flow control, hypersonics. A lot of these applications have been enabled by this sustained long-term support of the government. Thank you.
Okay. Okay, since we've been talking about how do we take CFD and apply it for certification, we thought it would be worthwhile to have someone that has really been through that process to have a discussion about his perceptions and opinions on how CFD would be applied. And when we say certification, I think everyone has a different interpretation of what that means. You know, how accurate does it have to be? As accurate as we get in flight tests? Is that more accurate than that? How capable is it today? And so there's a lot of things that we have to do in order to prove to ourselves, let alone the FAA, that we have a tool that can do that. So with that, I'd like to introduce Dr. Wilson Felder. He's the director of the Washington Operations and a distinguished service professor in the School of Systems and Enterprises at Stevens Institute of Technology. In 2012, he retired as the 15th director of the FAA's William J. Hughes Technical Center in Atlantic City, the nation's principal federal laboratory for engineering, research, development, test, and evaluation of air transportation systems. In this position, Dr. Felder served as the FAA's Director of Research, Development, Test, and Evaluation, and also co-chaired the Aeronautics Science and Technology Subcommittee of the National Science and Technology Council. Dr. Felder is a fellow of the American Institute of Aeronautics and Astronautics and served on the board of AIAA for 10 years, first as the director of the aircraft group and later as the vice president of standards. He is currently a member of the board of International Test and Evaluation Association, an instrument and rated private pilot. He retired from the Naval Reserve with the rank of commander and holds a bachelor's, master's, and PhD from the University of Virginia. He has written and lectured on the subjects of modeling and simulation as a component in test evaluation and deployment of new aircraft types and air traffic procedures. So, welcome. Thank you.
All right. But we only got a half an hour left. All right, so I'm really going to try to stick to 7 minutes. And then I hope I get a chance to make some additional comments later. I think this report is really a great piece of work. I congratulate the team that worked on it. It makes for fascinating reading. I encourage you to dig into it. What I'd like to do this afternoon is point to 3 important roadblocks I think stand in the way of achieving the goals set forth in the report. Only one of them has directly to do with certification, but I think they're all contributors. One, of course, is that any report in today's environment, and I'm going to boldly predict in any future environment that I can imagine, any report that calls for additional funding for anything is pretty much doomed to failure because let's face it, the truth of the matter is there isn't going to be any more funding unless you take it away from somebody else, and the nation is full of other groups meeting in similar conference rooms that are advocating spending more money on everything that you can imagine. So that funding reality is really going to cause us problems. Number 2, I recognize that this is a report chartered by my very good friends and colleagues at the top of the Aeronautics Research Mission Directorate at NASA. And so it is a very NASA-centric view of the world, and I think it necessarily has to be, because you cannot write a NASA report and recommend that the Air Force or the FAA take some action. However, I think it's absolutely critical to understand that this is a collaborative problem. It is not just a collaborative problem between NASA and the other agencies of the US government, both involved in aeronautics and otherwise. It's an international collaborative problem. And this kind of an aspirational roadmap is not going to be achieved unless we can bring those other parties, including industry, to the table and have them contribute. And in light of what I just said about the budget, it's clear that that has to happen. Finally, both of these things are particularly true if you intend to use analysis as a basis for certification. And I have argued repeatedly over the past several years that intense collaboration across agencies is absolutely critical. I will just suggest to you that to attempt to come up with ways of using analysis, including CFD, as a basis for certification without including the FAA as an integral partner in doing that work will make it extremely, extremely difficult. I hope I will have the opportunity to add some to these points as we address the specific questions that we're going to deal with on the panel starting right now. So I'm going to leave my introductory remarks at that. Thanks.
All right, thank you. We actually have till 4:30, so we have a little bit more time. All right, so what we're going to do now is we're going to have, we have a number of questions that we're going to ask, and we want you to participate and ask questions as well. But we'll get it started by some of the prepared questions. So I'll start with asking the panel, what are your top takeaways from the Vision 2030 report, and were any of the findings a surprise to you? So anyone want to go first?
Shoot, I'll go ahead and do it.
All right.
So I guess the one that caught my eye was in finding one, and it says we have to reinvigorate, you know, our R&T development. And I'm not sure that that's necessarily the right characterization, so to speak, of what we should do. I think it's more like we need to re-vector and we need to realign. I think reinvigorate kind of says we're going to do a lot of the same things that we've been doing in the past. We're just going to dredge them back up and reinvigorate them. Well, I don't think that's the right approach. I think what we're talking about here as far as the flow problems and the things that we're trying to attack are different enough from where we've been in the past that it takes a real step back and say, okay, we need to make some strong directional changes, realign with some different stakeholders, and start moving forward in a different direction. So that's my, that was one of my kind of takeaways that from the report that kind of caught my mind. And when I think about that, there's a lot of discussion in there. We talk about turbulence modeling. And in my career, when I started my career and started doing the first CFD codes, you know, we had kind of like flow physical problems, like physical phenomena, like shock waves and transonic flow. When we talk turbulence modeling to stakeholders, it's not going to resonate. It doesn't resonate very well with the people that we're trying to sell these things to and trying to get them to invest in our thing. So I really do feel like we need to come up. We need to focus less on the terms that we're all comfortable with as a community of CFD developers, and more towards the community of the stakeholders that we're trying to get the investment from. And so we need to talk about physical phenomena. We need to talk about separated flow. Sure, we need the turbulence modeling stuff to do that, but let's get out there in the front the things that are going to catch their eye and make them invest in us. So we could talk about that as a panel. I don't know if anybody resonates with that or not.
Cord?
Yeah, well, first of all, with respect to the report, I think it was a very concise report, and I think everybody should read it, and essentially you may present it, as you said, to the people who should come up with the money. The problem is, do they really understand the message? And I think this is what you wanted to mention. I think what has to be made clear is what is, on the one hand, the potential, and why should anybody invest in it? Since CFD, I think, is more and more viewed as a commodity. Well, it's working, so what? And what is the potential, say, in 20 years? What really can be gained by that, despite becoming, say, more accurate, tackling somewhat more complex problems, which is interesting for academia and things like that. But what is the real value of it? One of it, I think, was mentioned is certification. So what are then the requirements, really, of certification? And, well, maybe you will correct me, but I think with respect to certification, we are not talking about accuracy and things like that. We are talking about reliability. Since at the very end, somebody has to write his or her name under something and say, okay, it's proven. It's going to hold against all loads and things like that. And when we are talking about reliability, who in this audience here who has run CFD computation would at the very end write his name under something and say, okay, let it fly now, without any testing in front of it? And I think this is essentially what we have to address in the future.
Yeah,
how
build
do
that
we
confidence.
Build this, how do we become reliability? How do we become reliability into this process? And then we can sell it in the way, as you said, then we can really leverage the full potential of it, and then we get the revenue out of it. And I think this is how one has to address this problem.
Anyone else that want to add to that?
Well, I'm tempted to leap ahead to question number 3, but
Patient.
since you brought it up, are we allowed to do that?
Sure.
So question number 3 in your prepared questions had to do with how you achieve exactly this end. How do you get, and I thank you for bringing this up, because I think there are a lot of people who don't understand that in the end, in the process of certification, it is an actual human being, an FAA or EASA individual employee who puts their name on a piece of paper called a type certificate, and if they're wrong, then there's a huge personal impact to them for that. And so it drives a natural conservatism.
Right.
And so the question is, there's a break point. We can use these tools to inform our own design activities. And I think we were talking before we came up here that that is certainly something that's very important that we can do. Then the question is, how do you go beyond that and deal with the regulator? And I think maybe there are four basic steps that one might take to do that. First of all, you need to be darn sure about your model results. So there have to be points of calibration, whether they are with flight test or wind tunnel test or whatever, that build confidence in the reliability of the tool over a large envelope, right? So that's step number 1. Maybe step number 2.
And it doesn't have to be all at once. It's not everything gets certified with this process.
No,
You're
right.
going to take some baby steps along the way.
You have to take continuous baby steps. That's the incremental steps toward dramatically different end results.
Right.
And that brings me to number 2, which you and I were talking about earlier this morning, the idea that you develop the advanced designs using the CFD and other tools, but then apply them to engines or aircraft designs incrementally. So you find a way to put that new, as we were talking, I think, about the Gulfstream winglet, you do that incrementally. You put that winglet design onto a new airframe, or onto an existing airframe as a mod. You get that certified as a supplemental TC, and then build it into a future complete design so that you lead the regulator along that way. Number 3, we're getting to the point where some of these new designs are systemically complex. So it goes beyond just designing a wing. It all works together, especially when you talk about some of the morphing structures. One way to build confidence, and we certainly have done that with different sorts of air traffic control methodologies with UASs and so on, to embed those new designs into a sophisticated human-in-the-loop model simulation that you can actually bring the regulators then into a simulation and let them experience how that new design will play out. That's a third possible thing to do. And then, my other recommendation is to actually designate a national aircraft certification office that is dedicated to transformational designs, so that you would staff that office with people that perhaps had a little bit of a lower bar toward really radical and transformational designs, and then they would be more willing to work with you as a manufacturer to certify those those products based on more simulation and less ground and flight tests. So, you know, now whether you can achieve that, I don't know, but it's all a matter of making the regulator comfortable that what they're about to sign on the dotted line for is really okay.
I like the term that Cord used when he said in support of the certification testing. You know, think of it not as a replacement, at least initially, but build it up.
Perhaps is it on? Okay. Perhaps one remark with respect to this replacement, since this debate is going around for the last, I don't know, 35 years or something like that the CFD is going to replace the wind tunnel. I think one shouldn't talk that way. Think about it as a tool and use the proper tool for the right purpose, and that's about it. If the wind tunnel is a better tool in producing mass data, you can consider the wind tunnel as an analog computer. It's very good. Mm-hmm. So why replace it if it's good then? What you have to do is, if you really want to replace it by CFD, make CFD the better tool. But don't try to just replace it to replace it. It has to fulfill a certain purpose. And the same holds for flight testing. You only go to flight testing when there's no other way. Right. Since flight testing, if you've ever done it yourself, well, it's eating up a lot of money and so on. But sometimes you need it as a real proof at the very end. So whatever kind you can use to reduce the amount you have to do on the flight testing, do it as far as possible, but don't try to replace it in the first place. So it depends just on tools and
yeah,
purposes.
It seems a long way off to think of the first time an airplane is really physically flown is when it gets delivered. That might be a little...
Yeah,
there's some experience with that, yeah.
So, yeah, I'm reminded of a similar situation like this where I spoke first about the need for more simulation in the test and evaluation process. And I was followed to the podium by Major General David Eichhorn, who at the time was the commander of AVIATION. And his lead remark was, that's all very well, Wilson, but you know, sooner or later you have to fly the boop boop airplane. You do eventually have to fly the airplane, right?
Steve, did you want to add anything? Or?
Well, I think when I think of the topic of certification, with engines, we certify airworthiness of the engine. We don't certify aerodynamic performance. It's not a certification requirement anywhere. So when it comes to airworthiness, it's really about the robustness of the structure and its ability to withstand operational faults, as well as its ability to meet environmental compliance rules. And so aerodynamics is key from the standpoint of the loads the structure undergoes in its operation. And so today, I don't think this is a surprise to anyone, that the CFD is often used to evaluate the critical points in the flight operating envelope of the engine to determine the condition which we must test experimentally to verify its airworthiness. It's called a critical point analysis. So from that standpoint, it is in the certification process today, but it is not the primary means of demonstrating airworthiness. Right. Further, when we go through a supplemental type certificate at the aircraft level, an engineering change at the engine level, usually that's based on a comparative analysis of the design that actually went through the test, the analytical analysis of the exact physics of the problem, multidisciplinary, and then the proposed design solution and a comparative analysis. And oftentimes that's a conversation with the FAA about whether that is adequate or whether test is required. And it is from the viewpoint of the regulator, why is the regulator, whose number one job is airworthiness, why are they motivated to cut corners, to stretch? They're not doing the public any good by doing that. Their job is airworthiness and certification of airworthiness. And to trust the engineer's analysis is close enough, it comes to the risk conversation. And so from that standpoint, you know, I agree with Wilson 100% that we've got to be working with the regulators to make them understand the engineering processes being used and to allow them to be comfortable in the judgment they're applying based on the analysis they're seeing. If it's a black box and we give them a written report, no chance. Right. But going through it with the regulators, much better odds.
So Parviz, hold on a second. If I could, Juan, could we go to polling question 3? We'll get that going, and go ahead and make your comments before.
Well, again, as long as we're talking about question 3, I thought I'd just elaborate on that. First of all, with regard to experiments versus simulations, this has been an old view, and I think simulations and experiments have different roles to play, and I don't think CFD's goal should be to replace experiments. No question about that. And furthermore, I think when it comes to certification, validation, which means with experiments, remains a critical step. I think will always be. The issue of certification is complex because it is connected to safety, mainly. And from a CFD point of view, again, here, I think well, in fact, without even CFD, a general requirement for certification is to ensure quality control on simulations. This requires elimination of, as far as CFD is concerned, point of view, elimination of user tunable parameters, automation of the simulation process from CAD to solution, control of grid spacing, time step resolution, etc. And 4,
you mean we have to have standards?
Detailed validation is the 4th. And another point I'd like to point out here, again in CFD, another critical component is uncertainty quantification. That has to be embraced from the beginning so that the source of uncertainties are promptly identified and their effect is measured effectively.
Okay, so let's see what the poll says. So the question is, what concrete actions should we undertake now to make certification by analysis a reality in 2030? And it looks like a majority of people are saying establish aggressive targets for acceptable prediction accuracy, and that is for 2020, another one for 2025, and then on to 2030. So, great. Now, if you have some questions, feel free to step up. I'll keep going through our questions, but I wanted to give all of you a chance as well to go ahead. I don't think so.
Yeah, it is.
Okay.
I've heard a lot about analysis replacing certification, but maybe you guys all know it, but what is the payback? I haven't heard that. What is the amount of money that we are going to save? I think if we do not make that case, where are we going to get funding for that? In my experience, I had always to make a case, I'm going to save this much money.
Correct.
So give me this much money. And I haven't seen this case made yet.
Well, it's not a difficult case because when you, as I had mentioned earlier, the only thing more expensive than wind tunnel is flight test. It's an order of magnitude more expensive. And so any savings in time is actually a very significant savings. You know, we're talking about on a typical program. The flight test program is a pretty good percentage of the total cost of a program. And so there's a B behind the cost of programs. So anything that has, you know, you're certainly talking millions, if not getting into the billions in savings when you get to that. But you have to trade that with the safety aspect of it. It has to be safe. That is the ultimate, you know, you're not going to get certification if it isn't safe. So it becomes a little more of a difficult argument on how do we make sure that we're providing the same quality, the same safety of that we get from the flight test program. And I think that goes back to our earlier conversation. But I think it is a very clear value statement. The other part of it is just how quickly do you get to the point where the airplane is proven and is ready to be delivered. And I'll add that I think on the military side, there's a very similar process. It's not, you know, the FAA certification in many cases, but it is very similar. You have to go through qualifications. Any other questions? Everyone at once? Well, then
I was going to say that I think there are some challenges to that, to your statement, Rob, about that. And I think certainly SpaceX right now, in the development of their launch vehicle, is very much a flight test type organization. They are doing a lot of their, not certification, so to speak, but to some degree certification, but they have a very strong philosophy of flight test as opposed to a lot of subsystem ground test. And I think their philosophy is that, you know, we could test it to death and then go fly it and maybe find out we were wrong in all our tests to begin with, or we can just go fly and get around some of the testing. I think they have a different balance. And so I think it's going to be an interesting see how all that shakes out, because they are very much, in my experience, on a path that is more flight test oriented.
So I kind of think back to, you know, earlier I mentioned the return to flight assessment, and I'm not sure how that would have been accomplished without CFD. I don't know if there was any testing that could have been done that could have given you those sorts of results.
For
the shuttle return to flight.
Well, there was. You mean flight testing?
Right.
Flight test. Yeah,
there was component testing, right?
There was plenty of component testing.
Right.
Yeah.
There was component testing.
Yeah,
but to kind of validate.
And I think it's going to be very similar with certification. I mean,
right.
You won't be able to replace, say, all the flight test data, right? You can do incrementally, like we were talking about, over time, and even that's a lot of money.
Right.
Yeah, you're absolutely right there.
I think that's a major difference. They are using a lot of proven components, putting them together, and then maybe flight testing is the most efficient way of getting the final proof. It's different than designing or developing something really from scratch, as it was done when the engine company started and things like that. Since that's, I think, the major way of putting things together and making this rapid progress.
Anyone else want to add anything? Okay, we have a question.
Funding is always a problem. And although the environment is difficult, the RCA program was started not long ago. So I think if we get to the right ears, there is funding. So my question for the panel is, what can we do to either increase or get funding from various sources?
Actually, you might have been reading one of our questions. One of the questions, kind of to expand on that, is basically considering the current likely future near-term budget environment within government industry, what would you do to advance CFD flow physics technology development and bring CFD technology in the hands of the aerospace vehicle and system designers? So it's along the same line, but who wants to take both the question and the prepared one?
Go ahead. Sure. So the way I look at this is we need I use the term critical mass. We need to develop critical mass in areas that we can make a large investment and an impact in, okay? I'll just make an observation. Many of you, I'll take that back, some of you, I see a lot of young faces in the crowd. Some of you probably remember in the late 80s, early 90s, there was a huge investment in CFD development. It was like the hot topic in the late 80s, early 90s, okay? And I'm just talking from a external aero standpoint. So for that 10 years, we made huge gains in our capability. But then, in the early 90s, say mid-90s, it basically kind of stopped. And I think what we were doing was we were looking at what we had done in terms of capability improvements, and we spent the next 20 years essentially evaluating, validating, verification of that technology, okay? And so we're to the point now where we kind of understand what we can do with that technology. It's taken 20 years. But now we need to build critical mass again for the next wave.
The next step.
The next step, okay? And so I think you know, a lot of it is going to come to where we pull together different groups of people. Parviz, you know, mentioned computer scientists, mathematicians. All of that needs to be pulled together where we can leverage different organizations to build a project, if you will, that has enough funding to be that critical mass. And I think that's really the implementation question on how we move forward with Vision 2030 CFD.
Go ahead, Wilson.
Well, since I'm the one who made the comment about not being able to get the budget, I would like to suggest that in this particular area, it's very important to form a habit of collaboration. And in going through the report, I did a word search. I did find 34 references to the Department of Energy, but that was because we were talking about the HPC installations. I found 4 references to the US Air Force. I found 1 reference to the FAA, which was under the certification heading. I searched hard for NOAA, National Weather Service, and the National Center for Atmospheric Research, and I found no references to those. Remember, it's a NASA report. But every single one of those organizations does sophisticated fluid modeling and has capability and capacity to do that. It should be part of the group that tackles this as a national problem. And the only way you can, and that way you leverage all of those budgets appropriately. That's very hard to do. For the period from about 2006 to about 2012, we had a tremendous spirit of collaboration across the US government in the National Aeronautics Research and Technology Program, led by NASA, the Air Force, well, DOD, and the FAA, but including these other agencies, produced the National Aeronautics Research Plan, which is quoted or cited in this document. And actually included in that was an infrastructure study that looked at high performance computing across all of the agencies and its potential use to reach these goals. And that has kind of fallen on hard times. So personnel departing from those agencies going into industry, change in the national priorities set by the White House relative to science and technology, a trend away from the kinds of science and technology that I think we all care about in this room, and toward more of an emphasis on internet-based interventions in healthcare and finance, for example, which basically eliminated the slots at OSTP that were filled by FAA and NASA people to do the kind of coordination that we're talking about here. I think one of the things we need to do, yeah, going after more budget is great, but that's a very hard slope to climb. I think one of the things we need to do is reestablish our own habit of collaboration and find ways to leverage the work that each of us is doing. And the report itself says quite clearly NASA cannot go it alone. So let's bring everybody into the fold. I think, quite frankly, AIAA is in a position to help with that advocacy. When we talk about public policy, advocating for more funding for NASA or the FAA is lobbying. And those of us, I'm no longer in the government, but those of us who are in the government have trouble supporting that. But advocating for national collaboration on important issues is the kind of public policy we could stand up for as AIAA, and I think that's the way we get to the answer to that question.
Thank you, Wilson. Before you get going, why don't we pull up the audience polling question number 2 and see how all of you feel about this. Go ahead, Cord.
Yeah, perhaps coming back to HT's question about how getting the money, and also referring to your remark about this time in the 80s when CFD did not need any legitimation but was legitimated by its own. A lot of things came together at that time. The advent of supercomputers like the Gregg computers, then the first successful application of such type of code. So there was no need to legitimate why money needed to go this way. But it was also for the decision maker, it was very clear that it's a new opportunity, something which is exciting. So you didn't need to do anything. And time has changed. I think this is something which the CFD community really has to accept, that CFD by itself is nothing more than an activity, and there are many activities in the research community. So CFD is competing with everything else. And personally, I know this very well, since well, trying to find sources for money is more or less what I'm doing now. And from that point of view, I'm coming back to a question which was raised, I think, 20 or 30 minutes ago. One really has to make clear why should anybody who should provide money should invest this money, and what is the return of investment. And I think that's the major problem. And coming back to this issue of certification, it's not about performance. Performance has nothing to do with certification. On the other hand, if you talk about performance, if you look at today's, let's first talk about transport aircraft. In which way are you going to improve these? And which kind of tools do you need for that? Is CFD really a tool needed for that? If so, come up with the reasons why it is necessary. And then you may get the argumentation why you now need money to improve these tools. But just trying, okay, I have interesting ideas about CFD. Well, I think this is not sufficient anymore.
Well, certainly having a vision of where we could go with it helps to kind of pull that kind of information together. It gives you something to kind of shoot at and putting that story together of what it could be, what that vision of that future is. Otherwise, we end up kind of slugging our way through, and maybe we end up in the same place. But
but I think you need really a vision. What is the future application of CFD to gain vast improvements? Not about this business as usual.
We did a fairly decent amount of work in defining the CFD requirements in the document to go after what we think is going to be important in terms of aerospace design, vehicle design, say in 20 years. But you're right. I think it's very specific to the platform that you're looking at, right? As to what tools you need. I totally agree with that.
Can I make a comment on, and I'd like to give another scenario for the where we can get the funding, or where the money's going to come from. Just give you a little bit of perspective. I mean, when we talk at NASA, if we're asking, and a lot of the report says, what does NASA need to do to reinvigorate this, in my mind, revector it or whatever. And so I think if you're talking NASA, you have to kind of look at what you're dealing with. I mean, you've got an Aeronautics Research Mission Directorate that's funding virtually all the tool development for the agency. So when we talk about NASA funding, it's coming out of ARMD. ARMD carries about less than 3% of the total NASA budget. You've got, when you take out the overhead, you've got space, exploration systems, and space technology with the other 80% of the NASA budget. Those guys got big problems over there. And yet we're playing in the 3% pool. So I don't understand why we're playing in the 3% pool if we've got big problems. I can tell you we're going to have a lot of trouble getting to Mars. And a lot of it's not going to be Aerosciences issues, but the majority of the energy is expended and the majority of the energy is absorbed in coming in and out of the atmosphere. it's right in the sweet spot of where we can do CFD type analysis. And so I think there's going to be motivated investors out there, but we have to kind of play their game.
We have to tell that story to support it.
Exactly. I mean, when I see examples in this document, and when I see examples of separated flow, I see separated flow behind a landing gear. Well, that's not going to get Bill Gerstenmaier's attention. If you added, you know, smooth body separation on an Orion capsule, he might perk up and say, well, maybe this is something, maybe these guys are actually trying to work my problem. So that's really where I'm coming from there is there's a big chunk of the NASA program that we really aren't addressing very well with these types of discussions.
Which leads into another question that I'll get to in a second. But first, let's look at the audience response on what is the most effective approach to fund and sustain a CFD technology program. And over 40% seem to indicate the government-led consortium funded by government and industry is the most appropriate approach. So, interesting. John, there's a mic over here if you...
Even when I look at this survey question, it says government-led, but which government? I mean, we're talking about, up there I've heard national activity. This is an international problem. This is something we need to bring the whole world together on. And if the return on investment is best realized by industry, why isn't industry self-funding a international project? The survey disagrees with me, but I've been in that boat before. So I mean, that's just kind of a general question. Maybe that's the grand challenge: is how do we figure out how to work this out ourselves and fund it?
Good question. Parviz?
Well, again, I like to bring the recent experience that we have had, and 5 other universities have had too, that DOE's funding of major grand challenges that they envision. The first requirement was it be sustained. Second, they didn't just throw the money over the fence. It was subject, each program was subject to heavy scrutiny by expert scientists from the laboratories that came from behind the fence and actually reviewed. The universities learned a lot from them, how to integrate, how to do a big system, how to start introducing uncertainty quantification. They made that a target. It wasn't a generic goal, but a targeted goal, that next 5 years, we want you to come up with credible techniques for uncertainty quantification, verification, validation, how you, along the same lines that we are talking about here in terms of certainty. Then the next 5 years, we are going to move towards exascale. How you write your codes, new languages that would allow you to achieve that goal. So getting the right people under one roof, people that are cognizant of the computer science issues, they can bridge. We can't have multiple silos, computer science, numerical analysis, physical experiments, but the people that have is interdisciplinary as opposed to multidisciplinary. They learn from each other and they are interested in what others are doing in a different domain. I think that is critical in terms of making the major advances. And this has to be done under one roof in a concern and long-term support. And I think it has paid off. Certainly, most impressive. I mean, these folks have to certify the safety of the nuclear stockpile to the Secretary of Energy and the President of the United States. And it's simulation-based. So
okay.
We can learn a lot.
All right, Neil.
Hi there, Rob.
A ringer.
You know, my doctoral,
Don't pay attention to him. No.
My doctoral work in separated flows back in the 1970s was sponsored by the Boeing Commercial Airplane Company. It wasn't sponsored directly by NASA. I think that the only way that we have a way to get funding is to actually have the tax laws written such that the investment that the corporations put in has tax implications for them, and they can recover that money that way.
I think it's easier to go get more budget for NASA.
Administrators versus.
So I would like to add to that point. Again, there are many things that are resonating here. In oversimplified terms, I think this is a question of a group of very intelligent people who are running out of money and trying to bridge the gap between them and the people who have a lot of money who are just not particularly very smart, which is sort of the financier group. I've worked with them, so I know what I'm talking about. One of the points that came up was sort of the plateau of increased benefit in terms of additional efficiency versus the increased computational power. So that means that the tools continue to get better, but not necessarily the uses that we're deploying them for. We're not really gaining much in the way of benefits. And one of the things that I've personally been grappling with professionally is how to ask different questions. So by that I mean, if you ask the people who have the money what keeps them up at night, and you learn a few terms from the language they speak, namely long-term cash flows and bottom line, then you start hitting upon things that would allow you to unlock very important sources of funding. So for a very simple example, wind power and wind turbine design and generation is running a few years behind the aerospace industry, even though it's heavily dependent on it. But one of the things that wind generation companies are dealing with is how can they increase generation with the tools they already have. One instance in particular is they're dealing with icing on the blades and how that is impacting the generation capabilities. Now, one very important thing to take into consideration is that they do have, say, 20-year contract to purchase the electricity, and that has a very a very well-determined stream of cash flows going forward. Well, if CFD methodology is used in order to predict what increases in efficiency can be gained from that, then you're linking directly the initial cost of investment with a potential increase in the returns, which is what they think about all day long. Therefore, you turn that over to a bank, and you definitely can unlock funding that way, and that actually brings up the final point, which is everything that is done in that industry is based on the tax bill. So you can already very well address the problem of we're unlocking tax benefits from somebody else, but you already have the machinery. There's already a very well set sector, which is the financial sector, and there are definitely ways of sort of gaining access and just working to unlock those additional sources of funding. So that's a very long-winded point. And that's all I have.
So anyone have any comments?
Sorry about that.
It's all right. I will say that I think that there's strengths and capability in lots of the different organizations that bring different things to this kind of a problem. You know, you can be talking about fundamental physics that needs validation, and how do you mathematically model that? And I'm not sure that those of us in industry have, you know, a lock on all the people that are really smart at doing that kind of stuff. And so I think that there's a wide range of making sure that we have as much being brought to these kinds of discussions and findings as possible. And talking about collaboration makes a lot of sense, at least to me. And whether you talk about early part of the physics base or actually getting to the application, obviously that is a transition that occurs going from research organizations to industry. So anyone want to add to? Sure, go ahead, Steve.
So during this conversation, I think when we talk about funding and the challenge of funding, it's important for us to understand in the United States, aerospace is our #1 export. Right? It is the thing that causes the most positive trade balance we have. And we have an overall negative trade balance, right? This isn't a national imperative to protect our position. So politicians should think about that. We're not politicians, but administrators should think about that. How do we protect the American position in aerospace? Corey, don't take offense.
Well, and there's newcomers coming into that are going to be playing, obviously, a more important role as we move on.
If you look at what's going on in the commercial aerospace industry, aviation industry, you have Japan starting a national initiative to develop commercial airplanes. You have India talking about doing the same thing. You have Russia clearly trying to diversify their former industries into world-class commercial industries. It's a goal for many. So the industry is somewhat under attack. So from that standpoint, there should be the motivation for funding. However, the one thing I would say, and it didn't come out clearly in the report, is we need to differentiate between funding that's going to be used for the next turbulence model, and please don't take offense with that, versus funding that would be used to change the game. And if we're spending money on the next turbulence model, I don't want my taxpayers' dollars for it, okay? Because it's not really going to change anything. The problems we're talking about here are so challenging that more of the same will not get us there. We've been doing it for so long. What is going to change? So I think part of this has to be a prioritization of not just what we're trying to achieve and what we spend our money on, but the approaches we take. And the higher risk, higher reward approaches need to be filtered to the top rather than pushed to the bottom. Because the biggest gains ever taken or ever garnered are from the highest risk taken. You fail many times, but you succeed once, and look at what it gets you. Right? So if we don't take that approach, right, I think we're doomed for failure.
Yes, Gregg.
Yeah, well, perhaps making a comment on that. I didn't take any offense from what you mentioned. But let's assume for a moment that we are sitting in the boat, in the same boat. And I think not for the moment, but we are, if you take us as the West, we are sitting in the same boat. And as you mentioned, there is strong competition from the upcoming states in Asia. And what they are doing is essentially learning by doing. Their repetition cycle in developing new products is a lot shorter than what we have.
Absolutely.
And we have the privilege of being in a matured state, which means we get risk aversing. Yeah. And the question is, how do we then trigger innovation in the future? And perhaps you remember, I mentioned this in knowledge preservation. How do we ensure that the next generation of engineers is still able to design aircraft, having all the experiences which was accumulated in the past? How is this being done? In former times, it was a lot of people had, let's say, 5 or 10 aircraft development programs behind them, and then they were able to convey this knowledge to others. Today, I think, as I mentioned, you may have 2 or 3 if you are lucky. So how do we then compete in the future? And from my personal perspective, and now I'm coming with the selling argument, which was people are thinking for, it may be via a virtual product base, that by numerical simulation, which is not only CFD, you try to invent again this experimental phase without taking these large risks, spending money on hardware, on flight testing and things like that. And if this is, put it this way, formulated in the right way, then perhaps one can make the argument why it is necessary and wise with respect to the future to invest in that. And then you may get also at the very end the money for the turbulence model.
Parviz?
I think this is precisely the difference between the roles of government and industry. Government looks for long-term vision and maintaining the country's advantage over the competition. That's where high risk comes in. That's what the role of government. And I think industry, as far as I'm concerned, they have not even taken up because of the conservativeness that exists there and worrying about the dollars and cents every day. They have not even adopted some of the leading edge technology that exists already in there. They are slow in investing in HPC, high performance computing. They don't go out, the government, Department of Energy in particular, has offered very cheap rate, 1 million cores. I think less than 500 of a cent or something like that per hour. Industry doesn't embrace that here. We are giving a lot of computer time at Argonne National Laboratory to the Europeans. They write proposals and use this technology. So I think the role of the government should be to seek out these high-risk operations, gather the right people with the proper leadership. And the leadership goes both in terms of funding, BAAs that come out, what the grand challenge is that they're going to address, and stick to it. And let the bright Yankee engineers go solve it, and I think they will.
I will just add that industry tends to, because of risk, they tend to temper, they look at the benefit versus the risk associated with it. And if it has a high potential payoff, they're more willing to accept that risk. But they have to have, from an industry standpoint, you have to have ways of mitigating that risk, or else you're likely to lose your business.
If I may add one other thing. Years ago on the Center for Turbulence Research Advisory Board, one of the members asked me, who's your customer? And so CTR was the program funded by NASA for years. Who's your customer? That was a time that NASA strongly felt that the customer of NASA is industry. And I said that the customer of the Center for Turbulence Research, certainly, or the government, is future generations of Americans and maintaining competitiveness of the United States. That is, I think, our customer, the government's customer, that we should focus on.
Okay, we're getting close to the end here. Let's see, I'm going to go to a shortened question on question number 4 for the panel. And we were talking about collaboration and how that might be beneficial. Do any of you have a feel for how do we enable a robust collaborative environment where we can really have multiple entities working toward a common vision, including international participation? Go ahead, Steve.
I actually think there are many examples where this has been done successfully. And it tends to be in areas that are considered pre-competitive. And a lot of what we're talking about here, for many purposes, is pre-competitive because it's something 15 years out. So there's an icing consortium right now because the industry faces icing issues, right? There are SAE committees working on techniques on particulate matter that are well attended and being contributed to by the international community. So there are examples where this has been done. What that construct dictates, though, is that it is at a pre-competitive level, so it would limit the scope of what you could do. But I think we have to ask ourselves, is that where we start? Because a lot of these relationships are about building trust amongst the participants and really getting the activity going. And the pre-competitive nature is what is needed right now to get it off the ground. And then from there, the question of how you reduce it to practice at any industry point is really the industry's job, right? NASA should not be paying for the industry to develop design tools.
Right.
Right. So from that standpoint, it's very easy to see how this could be put together. I think the more challenging part would be about the priorities on what we work on, the funding levels, and the time frame. But I do think reasonable people put in the room, considering the problem, can reach an agreement.
There's also a point that you made earlier, and I want to emphasize that the roadmap that we see in the 2030 vision is quite comprehensive. And so maybe under the heading of collaboration, one of the things that we ought to look at is what elements could be taken out of that roadmap and become part of an industry consortium working in a pre-competitive sense with their own research investment dollars to pursue those elements, while NASA could take on some of the more perhaps riskier, farther out, bigger payoff in terms of long-term competitiveness issues. And again, I'm going to beat the same drum. And maybe let's see what DOE is doing that has transferability to our world. Let's see what we can get out of the Air Force. AFRL has its own high-performance computing system. Can we use some of that? Are there some things that DoD could be doing? Are there some things that the FAA could be doing? And in my notes for this question, I say, well, the fluid flow is fluid flow. There's some of these problems that maybe the U.S. Navy might be interested in working on.
And we can't forget that there's also helicopters, and so there's...
Yeah.
Helicopters are aircraft.
Yep, that's right.
We like helicopters.
I mean, we don't have a representative for helicopters, but...
Oh, I have 1.8 hours in helicopters. Yeah, they're good.
So Rob, I have an idea. I haven't really kind of thought this out, percolated on it.
And as you're doing that, Juan, why don't you pull up the polling question number 4? Go ahead, sorry.
Okay, no problem. One of the things we can do is play off of human nature, okay? We're all competitive. And I think we've seen good examples of what we call the X Prize. And it seems to me that if you had an X Prize-like incentive to work on some of these problems, where perhaps a team led by academia, would compete over time, maybe a period of 5 years for a certain amount of money. Obviously, the incentive is money. The incentive is prestige and pride, right? That you can maybe, tackle maybe a grand challenge problem with an X Prize-like incentive. I'm still percolating on that, though. I'm not sure if that would really work in a researchy environment, but maybe.
We actually looked at that possibility on the National Aeronautics Research Plan. What's hard is picking the challenge that is worthy of the X Prize. How do you define the goal so that it's clear, meaningful, and not necessarily achievable, but so that you know when you've achieved the goal. It's hard to find something as compelling as the actual X Prize. The definition on that was pretty obvious. So how do you translate that to this problem would be a difficulty.
But I think coming up with different ideas of how to encourage work in this area is certainly something we need to be spending time at.
Something we've been pushed a little bit towards at NASA is these crowdsourcing things where you put out a problem and you put out some fairly low amount of money and you just send it out to the world, and they have a certain amount of time to send you whatever, and you get some really crazy ideas, but every once in a while you get a nugget. And so we've been trying to, I think our medical community at NASA has done a really good job, and they've actually, and as well as some of the human factors areas at NASA have been able to get some really good and innovative ideas about how to solve a problem that they just never thought about just by going to these crowdsourcing things. So, you know, kind of akin to an X Prize, but maybe on a lower, broader scale. It's, and again, I think it's about formulating the problem right, though, you know, because you don't, if you formulate it bad, then you don't get anything but garbage. So.
Right. Gordon, you were going to say something?
Yeah, well, I can talk to you only about international collaboration. And well, perhaps, but let's, if I look back, and maybe that's the reason why I'm sitting here at all, is first, I think one has to identify this pre-competitive topics, which I think is quite essential. And then I think one has to create a certain environment for personal exchange, and personally I benefited substantially from iCase in the former times. Maybe that's the reason why I'm sitting here at all. And I think then one has to provide access to computation and experimental facilities that these people can work. And I think that's all what's needed.
All that's needed. Okay. All right, it is a little after 4:30. We went just a little bit long. Questions that we wanted to cover that we didn't have time was talking about HPC requirements and where are we going. And then if we had time, MDAO, but those I think are ones we'll have to save till later. I do have a recognition for all of the panelists. I think it was a great panel. I hope all of you enjoyed the discussion. It looks like we kept most of your attention, but we have a little coin, a token of recognition for serving on the panel. So thank you very much. If everyone will give the panelists a round of applause. Thank you.